Welcome to this special edition of Elektor Engineering Insights, directly from the PCIM trade show here in Nuremberg. I'm here to discover what's going on in the power electronics industry and find out why power designers have been coming to this international trade show for more than 40 years. Inside we'll see power semiconductors, passives and other components, test equipment and the applications that are moving power efficiency to their limits. We'll be looking at motor inverters with high efficiency and finding out more about smartphone chargers that would take the time required to charge your phone by 50% down to just 15 minutes. I've been talking to MinDCet CEO Mike Wen, finding out a little bit more about their approach to power conversion designs. High efficiency is obviously a key factor in today's technology, especially with all the switching converters that are coming onto the market and with a view to all the wide band gap technology that improves device efficiency. MinDCet develops ASICs specifically for high performance power converters. But another critical aspect that they discovered during their development of their company was that often the efficiency depended very much upon the inductors and capacitors in the design. This led them to also move into the area of test equipment with their MADCAP and MADMIX test equipment for inductors and capacitors. Those devices today are used by some of the biggest passive component manufacturers in order to provide their customers with the insights they need to make highly efficient power converters. Alongside that, they've also been working very closely with the space industry to implement a range of GaN drivers. The advantages of GaN only come when you're able to switch the switches exceptionally fast. That means high rising and falling edges and making sure that the drive current and voltage applied is accurate every single time. Now, the space industry is not known for forging ahead with new technology, but in this case it's completely different. They're looking to the advantages that GaN bring in the areas of long-term reliability. That's why they're so interested in the latest GaN Buck Converter. Now, with MinDCet's MDC901 Buck Converter, space industry has been able to deliver high performance power conversion for satellite technology. Of course, it's not in space yet, it's still being developed and integrated into the system. But that technology can also be rolled out to other players who are looking at GaN to improve the efficiency of their converters. They're also developing new drivers for SiC devices. An example shown here at the show is a 250 kilowatt power inverter for motors. Those are targeting the excavator industry, an industry that's looking to move away from fossil fuels as far as possible and adopt electrical power in some of the drive systems in those equipment. The interesting thing about SiC for them is the high switching frequency it offers, which gives them the ability to control the wheels of the vehicle very, very accurately. And that's not surprising that they want to do that, because those wheels at 2.4 meters in diameter cost around 40,000 euros each to replace. So they want to make sure those wheels give a full service life. Now, it's always interesting to see a little skunkworks project come out into the open, and that's exactly what you see here with the MADAMP GaN-based amplifier. GaN provides such high switching accuracy and speeds that the level of distortion is minimized significantly compared to developing Class D amplifiers with other silicon-based switching technologies. The story here is that there is a lot of work going on at the minute in Europe and North America to push GaN into high performance, high-end, hi-fi equipment. Whether it will see the light of day in other areas like flat screen TVs and soundbars is yet to be seen, because GaN switches are a little bit on the expensive side at the minute. However, the feedback on this particular amplifier so far has been exceptionally good, with hi-fi enthusiasts giving it a good thumbs up. Now, PCIM isn't just about power semiconductors and components, it's also about connectors. in order to link together the power electronics with various different types of applications. Now, electric vehicle charging has become one of those big applications where everybody is looking to implement it as best as possible. And Phoenix Contact have an excellent display here showing the various ranges of connectors for vehicles and how to implement both an AC and DC vehicle charger. Their CHARX range of products covers surge protectors, DC power converters, charge management, and all the other elements that are surrounding the charging application for electric vehicles. And it's the type of system that you're going to be seeing soon more frequently built into commercial buildings and also the home. PCIM Europe is a great opportunity for manufacturers to display the latest and greatest technology. That's why I'm here with UnitedSiC, now Qorvo, to talk to Anup Bhalla about the 1200 volt SiC MOSFETs that they're launching here at the show.
So we're on our 4th generation of silicon carbide technology over at United Silicon Carbide, which is now Qorvo. We launched a 750 volt class of products about a year and a half ago at the end of 2020, and since then we've been just deploying them in other packages, and now we're raising the voltage class that we're offering. So we brought the Gen 4 technology to 1200 volt, and we are releasing the first devices in that series. These are devices from 23 milliohm, 30, 53 and 70. This milliohm class of 1200 volt devices finds a lot of homes in the onboard chargers and DC-DC converters that need to work from an 800 volt bus in EVs. Of course, it has a lot of other applications in inverters and solar systems and other UPSs, things that work from that 800 volt bus or 600 volt bus where you can't use low voltage FETs. So the Gen 4 technology, it's an evolution of semiconductor technology where you're able to get the same functionality and the same kind of converter done with a smaller chip. And then a smaller chip gives you the same low RDS on, but it's smaller, so it's got less capacitance and it switches faster. So you can see how things get more efficient. And then you can shrink your magnetics and do all of those things. And you've got the hassle that the chip's smaller, now you got to deal with the thermal. So we've got to do a lot of engineering to improve how we make it, so the thermal resistance we deliver is good enough for you to be able to construct your system, get everything to work, get all the efficiency benefits and deal with the heat management.
So what are the biggest challenges when moving from 750 volt SiC to 1200 from a development perspective for you?
Most of the work is done even at the 750 volt. The additional difficulty in making 1200 volt devices is to make sure that the packaging materials you use, which are coupled with the semiconductors you make, are reliable enough that at these higher voltages everything still works, and especially when you're supporting high voltage and you need 25 years of operating life. So mostly around the packaging, not so much around the semiconductor technology. We're very good at that.
Yeah. So that problem solved is just getting the packages right.
Right. So as you scale devices, that they remain good enough thermally and against environmental effects, so they're reliable.
The devices are being launched here this week at PCIM Europe. When should we expect to see the first applications come to market using the 1200 volt SiC MOSFETs?
So, we already are designed into a lot of onboard chargers, DC-DC converters and EVs. So this is more or less an evolution of those devices from that perspective, because they can help you do your next onboard charger more efficiently than the last one. That's one application. We're already in a lot of industrial battery chargers, whether they're for forklifts or for Amazon robots, these kinds of applications. Again, it's an evolution, so you do your next design better than the last one. I think these things all take different amounts of time. Industrial designs 1 to 2 years to ramp to production, automotive ones longer. So it depends on the application space. And solar inverters, energy storage systems are more industrial, so 1 to 2 years. So that's how long it would take for the devices to get implemented into a design and really ramp up.
What is it at the application level that's driving this need for 1200 volt SiC MOSFETs?
Well, the main driver was the desire to move to higher voltages in EVs for all the reasons you know about, because it makes, then you get half the current. If you're double the voltage, you're at half the current, which means all the copper losses go down. The motors even become more efficient. So it's a good way to make high performance cars. And then you can charge faster because it's 800 volts, right? So that was the main driving force. And when all of this infrastructure exists and the devices exist, these same benefits can be brought to a lot of industrial applications, because the converters are more efficient if you can run off of 800 volts. So we do have applications across the board now for these kinds of things.
And is 1200 volts the limit with silicon carbide, or should we be looking to see more devices come onto the market in the future that can handle higher voltages?
I think you'll see higher voltages because silicon carbide gets increasingly differentiated from silicon in performance the higher you go in voltage, right? And also that's territory that GaN is not really able to tackle now. So you've seen that there are 1700 volt devices there now. There are some 3300 volt products there now, but that area will grow, I'm fairly sure, in the future. The 1200 volt by no means is the limit.
Now RDS-on is obviously a big selling point of silicon carbide. Why would I not choose the lowest RDS-on for my application? What is it that's stopping me going straight for the 20 milliohm domain?
Yeah. You choose RDS, well, there's two factors. Just like with silicon MOSFETs, if you choose a very low resistance device, it usually has a bigger chip. If it's got a bigger chip, it's got more capacitance because there's just more area. If you've got more capacitance, the switching losses will generally be higher. So you've got to balance this in your application. If you're switching at a very high frequency, it might in fact turn out that the lowest resistance device is the wrong device, right? And so you've got to balance that, and sometimes you will choose a higher resistance device. From a switching loss point of view, you could go very high in resistance, but then you may not be able to dissipate the heat. So once you finish balancing these three factors in your design, you find that you need what we offer, which is a portfolio of options from very low resistances to fairly high resistances, because a different one may work depending on the particular situation you're in.
Super. Thanks very much.
You're welcome.
Also on the stand here at UnitedSiC is an application for driving motors from the company Pre-Switch. The CleanWave inverter operates at a switching frequency of 100 kilohertz using SiC MOSFET technology from UnitedSiC. In addition, to achieve its high level of efficiency of 99.5%, it makes use of an artificial intelligence or AI algorithm in the switching technology. That also helps it to achieve its power density of 203 kilowatts per litre. Now, power semiconductors and power modules play an increasingly important role in the automotive industry, as we see here with this e-scooter from Piaggio. It includes a 48-volt battery, which requires an efficient battery management system, and then a selection of high-efficiency MOSFETs for the power converters and the inverter for the motor control. That makes sure that you can get to your destination on time and still have enough juice to get home. Now, it's very tempting to think that digital is the only way to achieve maximum efficiency, but here at OnSemi, we're seeing some alternative approaches based on mixed signal analog solutions for high efficiency power converters. The advantage of an analog mixed signal controller for their power converters means that you don't need a digital designer and a software programmer on the team, which avoids the need for continuous firmware updates to keep the application going. So the analog designer can work on their own as they used to and bring devices to market more quickly. Two reference designs that they show here on the OnSemi stand today are USB chargers. One is a 65 watt application, which achieves a power density of 26.5 watts per cubic inch, and a 100 watt version with 24 watts per cubic inch. Their analog multi-mode converters are also used in higher power applications, looking at 500, 1000 and even 3000 watts. Intelligence is also an important part of power applications. which is why they've introduced the ECS640A. This is a motor inverter solution which includes the three-phase gate drivers, the current sensing, and a Cortex M0 Plus core, which functions as the microcontroller intelligence of the application, allowing status of the solution and any fault conditions to be shared potentially through IoT communication channels. Now, while wide bandgap technologies such as GaN and SiC offer improvements in efficiency and power density which lead on to things like smaller and lighter applications, there are some industries which are still held back by the price. Now, this is something that InnoScience is trying to address with their GaN switches. They looked at this application space very early on and decided that the best way in order to keep the price under control was to move directly to 8-inch wafer technology. Compared to some of the competitors on the market that are still restricted to using 6-inch wafers, this means that they get a 1.8 time increase in yield, that's the number of die per wafer, compared to using 6-inch technology. The other advantage is, of course, that 8-inch wafer fabrication processes are newer and more up-to-date, and that allows them to increase the yield and the reliability of the GaN switches that they're manufacturing. Talking here today to Peter Rogerson, it's also clear that the chip crisis of the last 2 years due to Corona has had an interesting impact on GaN technology. Many power designers who've been unable to get power MOSFETs made in silicon due to lead times being more than 50 weeks have turned immediately to GaN and absorbed the extra cost due to the lead time being well below 20 weeks. Now, currently, of course, GaN is a more expensive technology compared to silicon MOSFETs. However, there's some application spaces which are prepared to pay a premium. One of those is, of course, smartphone charging. Now, they have a partnership in place for a controller solution, which together with their GaN switches can actually charge your phone by 50% in around 15 minutes, using the latest power delivery specifications from the USB organization. Now, automotive is another space which will see increased use of GaN over the next years. And this is because even in today's electric vehicles with 450 volt batteries, there's still sometimes a 12 volt lead acid battery providing power to internal systems such as the multimedia and audio system. Of course, this can't go on forever. It makes no sense to retain that battery. So the automotive industry will be looking to GaN more often in the future to make the highly efficient power converters required to supply the voltages required for those types of systems. Nexperia is probably one of the largest startup companies in the world. Having been spun out of NXP 5 years ago, it currently does a turnover of over $1.1 billion. Now, you may not know exactly what Nexperia does, but they're probably in every application that you have in your home. They're responsible for a whole range of different types of discrete components, from surface mount diodes to MOSFETs and other types of power devices. One of the interesting aspects of MOSFET design is that most companies are continuously trying to improve the performance of the MOSFET in order to achieve efficiencies for all types of power conversion applications. However, there's a whole host of switching applications that don't actually benefit from all of those improvements. This is why Nexperia, according to Chris Boyce, who I was speaking to earlier, has been focused on some application-specific FETs. These devices use changes to certain parameters of the MOSFET in order to prove their performance for specific applications. And one of those is airbags. In airbag applications, the MOSFET is used to power a squib, and the squib is the part of the airbag which causes the airbag to inflate. The problem is those squibs are controlled by MOSFETs, which are today typically very old on old process technologies and using old types of packaging. The work here at Nexperia has been focusing on improving the performance of MOSFETs specifically to control that squib. That means adjusting some characteristics to improve it for powering the squib, but at the expense of other areas. One of the problems over the years with MOSFETs is that the safe operational area has come down, and this makes those types of devices unattractive for airbag applications. Nexperia has developed their application-specific FET for airbags, increasing that SOA in order to make sure that the automotive industry can also benefit from small packaging and latest technology for their devices. Another key important component in power converters are the diodes, and they can be handling several amps of current at any one time. The problem is trying to get the heat out of those in order to increase the operational current. Nexperia is working with a new packaging technology called clip bonded flat power, or CFP. CFP utilizes a sandwich technology with copper, a copper base and a copper surface, and in between the silicon is laid, and over the top the epoxy is molded to complete the device. These devices can be then much smaller than traditional diodes, saving space and improving power density for applications in automotive such as ADAS, LED lighting, and also DC-DC converters, and also in electric vehicle applications in the traction inverter and battery management. A diode in an SMA package requires around 13.5 square millimeters on the board and can support 6 watts per square centimeter. But moving to the much smaller CFP package, that can be as small as 3.45 millimeters squared and supports 20 watts per square centimeter. Now, component manufacturers sometimes make outlandish claims about their components, but here we have seen an application where 200 amps actually passes through a MOSFET. The MOSFET is controlled via a button to turn it on and off, and even with speedy switching, it still functions correctly as expected. This demonstration shows what is possible with some of the modern packaging technology and silicon device achievements that have been attained over the past few years. Now, the electronics industry and semiconductor industry make transformative technologies, and it's a very exciting field in which to work. Talking to Chris Boyce from Nexperia, the Senior Director of Marketing for MOS Discretes, explained to me that there's around 400 or more jobs currently open at Nexperia in a range of different positions. Well, that's all we have time for today for Elektor Engineering Insights special from the PCIM trade show. I hope you've enjoyed seeing all the insights into new wide bandgap technologies and semiconductors, electronics, and efficient power conversion systems. Keep your engineering questions coming in, and we'll be looking forward to answering them in the next show.